So what I like to do is go over the topic of oscillations. So this is from chapter 14 in our book of the College Physics by Knight. And so if I start in the first section, 14.1, then this is basically going to give us some definitions of what an oscillation is. And so as an example, consider that I have a bowl, and inside this bowl I put a mass. It could be a little ball, and this ball, under the force of gravity, is going to roll down to the bottom. But now it has a certain amount of kinetic energy to it, or momentum. You can think of it either in the kinetic energy or the momentum. But let's say kinetic energy. It's got some kinetic energy, which is proportional to its velocity squared. So since it has the velocity, it's going to take that energy and keep rolling. And it's going to roll until it reaches some point. And then all of that kinetic energy turns into gravitational potential energy. There's no more velocity, so it stops. But now gravity is pushing down on it, and so it's going to roll back down the bowl again and start the process over again. And so it's an oscillation because we start at position 1, we go to position 2, and then we go to position 3. And once we're in position 3, we reverse the process and go down the bowl, and then now that we're at the bottom of the bowl, we have a certain amount of kinetic energy, which makes it keep going up, and it's going to travel up to the bowl until eventually it stops back at its original position of position number 1. And so we can label these. So positions 1 and 3 are the maximum displacement, and position number 2 is what we would call its equilibrium position. Two is equilibrium because if we just took the ball and left it at the bottom, it's not going to move. It's going to stay there in equilibrium. And so that equilibrium position is kind of its middle point. It's a midpoint between the max displacement of 1 and the max displacement of 3. So it's the point where if you just put it there, it wouldn't move. There wouldn't be any gravitational potential energy to transfer into kinetic, and there wouldn't be any kinetic energy for it to actually crawl up out of the bowl. So what's going to happen now is if there are no frictional forces or any kind of dampening forces, if there aren't any forces to take energy out of the system, then this thing will just oscillate. It'll move from position 1 to position 2 to position 3, back to position 2, back to position number 1, and so forth and so on for the rest of time. And so it's oscillating. It's in a fixed range of positions, 1 and 3, and it's just going to keep moving back and forth between those two maximum displacements. And so we can also define something called the restoring force, which is going to be this force which is always going to try and bring it back to its equilibrium position. So in this case, it's gravity. Gravity is the restoring force. Gravity is pulling down on the object in the y direction, let's say. And so since it's inside the bowl produces a normal force, which makes it fall along the surface of the bowl. And so really there is this component of gravity along the surface of the bowl, which is pushing it to equilibrium position number 2. And so no matter which side you're on the left-hand side or the right-hand side, there's always going to be a component of the force of gravity, which is restoring it into its equilibrium position. as long as it has that, as long as it starts at a position away from equilibrium, it's always going to oscillate toward equilibrium and then away and back toward equilibrium. So we can try and quantify this a little more and say, look at the time. What is the time that it takes to go from position 1, then to position 2, and then to position 3, and then back to position 2? So if we look now at the effect of time on oscillations, then we can basically look at what it is, the time, or we can define something called the period, which is the time to move from a starting position and then go back to or return to that starting position. Which I think we've seen periods before, where in this case we looked at circular motion, where for the circular motion the period was, if this was the starting point x, then it's going to go around the circle until it gets back to that position x. So that's its period. The period is the time to go one full revolution. In terms of oscillations, we're not actually moving, you're not always moving in the same direction. We're moving, in terms of the bowl, we have our starting position 1, and then it moves, and then it goes to the position 3, and then it moves back, and then we go back to position number 1. And so the period now is the time it takes to go from starting position 1 right here, and then go return to starting position 1. And so that's what the period is. If I just give it the symbol T, like we always have. Now we can also think not necessarily in terms of the period, but how many times the object will oscillate from its starting position back to its starting position in 1 second. So that's referred to as the frequency. So basically the frequency, F, is it moves one full length, or it moves one full, it goes from its starting position 1 over to 3 back to its starting position 1, so one cycle in the amount of time of the period. So if it took 1 second for the object to move from 1, go out and come back to 1, then we would have a frequency of 1 over 1 second. Anyway, so that is the frequency we can define as moving one full cycle in a period of time t. So the units on frequency are 1 over seconds, or the hertz. So a frequency of 1 hertz means 1 cycle per 1 second. A frequency of a kilohertz would be 1,000 cycles in 1 second. Okay, so the last thing I can say in this section is, well, what if we wanted to, we're trying to build up an equation, a mathematical way of describing this oscillatory motion. And so if I go back again to my my object in a bowl, so it starts at position 1, goes to position 2, stops at position 3 and rolls back, and then goes to position number 4, and then from there 4 goes back to 1. So the interesting thing is that this example I'm having of a ball rolling down in a bowl has two directions of motion. It's moving up and down in the y direction, but it's also moving in the x direction. So if we just measure the x direction, then what we would find, if we call the center of the bowl x equals 0, is that it starts at some position, we'll call it x max, minus x max. Actually, let me make this bigger. It starts at some position minus x max, and it goes to 0 at 2, and then it goes out to a position positive x max, and then it returns and goes back to 2. This is position number 4, and then it starts the beginning and starts the whole process over again. So what it's going to do is it's going to go back and forth, back and forth, back and forth between what we're going to call the amplitude x max. X max is this maximum range that it has to its motion. If we now were to plot it in terms of time, the x, so now we're plotting x. We're starting at minus x max at time 1, and then at 2, we get to x equals 0, and at 3, we get to positive x max, and then at 4, we return back to the equilibrium position of 0. So what we're going to find is that it's not linear, but in terms of position, when it moves kind of slowly to start off, and then it speeds up, and then it speeds up some more, and then stops, and then it slowly moves and it speeds up. So what we get is something that's more of a sine or cosine wave. We're going to get sinusoidal motion. So the equation that governs an oscillation, or how something is going to move in these particular cases, is going to be a sine wave. So we'll look at that in upcoming lectures.